So now that we know how to create a galvanic cell, one thing that we want to do is that we want to determine for any particular cell what the cell potential is. We're going to need some reference state in order to make these measurements, and we will talk about that in a minute. But we have to sort of compare them against the same thing. We're interested in knowing what the cell potential is because the larger the potential difference, the stronger the tendency for electron flow and sort of the more useful that cell might be. So a larger potential difference, and we can think about this sort of as the gradient in a river, right? The steeper the river, the more tendency for the water to flow. Same thing here. The larger the potential difference, the stronger tendency for electron flow. So for an electrochemical cell, the cell potential is just the collected difference in electrical potential for all reactions. And by all reactions, we mean the reduction half reaction and the oxidation half reaction. And we can think about this in another way, sort of as a measure of the energy available to drive charge. Between electrodes. And this is measured in volts. And just as a reminder, a volt is 1 joule per coulomb. So let's look then at the reference states that we use in order to measure the electrode potential for any particular half reaction. So remember, the electrodes are the anode and the cathode, and we want to know what the potential is at either of those. So any particular half reaction has its own unique standard electrode potential. But this is not something that we can measure directly, and so instead we measure them compared to some reference electrode, and generally the tabulated values are measured compared to the standard hydrogen electrode. And the standard hydrogen electrode has an arbitrarily assigned value of 0 volts. Right? This is sort of like when we talked about enthalpy and we said we just assign the enthalpy to be 0 at 298. So the standard hydrogen electrode, which is what this is, this serves as our reference electrode. Right? So let's take a look at what that looks like. So here is the standard hydrogen electrode, and because hydrogen isn't a solid, we use hydrogen gas, so the hydrogen H2 gas goes in and the turns into H plus ions and gives off electrons, and we need to have this inert metal in here basically to act as a conductor for those electrons. So if we pair a different half-cell reaction with the standard hydrogen electrode, then we can find the reference potential the standard electrode potential for a different half-cell reaction. Let's take a look at how that works. So the overall cell potential is determined from both the oxidation and reduction half reactions. So the total cell potential is the potential for the oxidation half reaction and the potential for the reduction half reaction. So we can look at this example down here, and we see that hydrogen is being reduced. So we have H2 gas going in, and we have H+, and that's forming H2 gas through this reaction. And we have zinc being oxidized over here. And if this circuit is set up with a voltmeter in here, then we can compare the potential for the oxidation half reaction to our standard hydrogen electrode. And we see that for this oxidation of zinc, the voltage that we read is 0.76 volts. Now, in general, these are tabulated as reduction potentials. And so it's for the reaction written in terms of a reduction. And so the reduction of zinc is actually just the negative charge of this. So for the reduction of zinc, it's negative 0.76. And I should make one more comment about the standard cell potential. So for standard cell potential, this is assuming that we're operating at 1 atmosphere, 25 degrees C, and that the activity of all species is 1. So that's the standard conditions, and later we'll talk about non-standard conditions. Let's take a look at the table which shows all of the reduction potentials as compared to the standard hydrogen electrode. So here's the table. It's a little bit difficult to read because the numbers are so low, but you can see this is the standard reduction potentials at 25 degrees C. Right here in the middle is the standard hydrogen electrode, which you can see has a value of 0. These things are then listed in decreasing cell potential. So some of these are negative, some of these are positive. The ones that are more negative means that it has a greater potential energy for the electron at the electrode, and it has a higher tendency to get oxidized. So down here we have a high tendency to get oxidized. Up here we have a higher tendency for the atom to be reduced. And if we look at the list, the highest one up here is fluorine gas, going to F-, and we know that fluorine has a high electronegativity, and so fluorine really actually wants to give up those electrons, or sorry, to gain those electrons and to go to F-, and so this really wants to happen. So the reactions that are on the top half here, these sort of want to occur in the direction written. And these ones down here have a natural tendency to occur in the opposite direction. So if you have a galvanic cell and you want to know, or an electrolytic cell, but if you want to know what the total cell potential is, you find the reduction reaction and the oxidation reaction on here. You identify the potential for that cell, and then you can find the cell potential. So let's look at an example of how that works. Okay, so let's look at the reaction iron solid plus magnesium 2 plus going to iron 2 plus magnesium. So for the reduction reaction here, we have Mg2 plus going to Mg solid. And in the table, we can find that the potential for this is negative 2.37 volts. The oxidation half reaction here is iron going to Fe2 plus, and the oxidation, it's the negative of the reduction one, so in this case it's 0.45 volts. So to find the total cell potential, we add those two up. And this gives negative 1.92 volts for this particular cell. Okay. It's also possible to use other reference electrodes besides the standard hydrogen electrode, and some of these possibilities are described in the textbook.